Hey everyone, welcome to End Behavior of Polynomial Functions. This is Nicholas JMV. So in this lesson we're going to talk about how to determine the end behavior of these functions, okay? So the idea here is when you talk about end behavior, you're looking at what's happening as x gets really large in both the positive here and negative directions. And essentially what happens is you're looking at the y value of the function. So when x gets really big positively, what's happening with y, and when x gets really small towards negative infinity, what's happening to the y value. So end behavior is all about the y value. And there's going to be there's four cases here. And we're talking about the idea of a polynomial. So you should be familiar with this. So when your degree is even and your leading coefficient a sub n is positive, you have up. So this would be an example like of the x squared, an x squared function, x to the fourth. So your degree is even and your leading coefficient is positive, okay? So we call that up. So that's a notation we can use. When it's down, you still have an even power, but your leading coefficient a sub n is negative. We say that's down. So when your power on your leading coefficient is even, notice that the end behavior is both going in the same direction, either up or down. Now when n is odd, the end behavior is going opposite direction. So when n is odd and a sub n is positive, we go down, up, right? Y is going down here, y is going up here. And when a sub n is negative, it switches, it flips, okay? So when the leading coefficient is negative, you have up, down behavior, so up, down behavior. And so what we're going to do is look at polynomial functions and look at the power and the leading coefficient to help us determine the end behavior. On a quick note, we're also going to be able to describe these end behaviors using what's called limit notation. So every polynomial whose degree is greater than or equal to 1 is going to go to, the y value is going to be infinite. It's going to go to infinity as x does. And we can write the notation as the limit as x approaches infinity. What's happening to your y value here? Is it going to plus or minus infinity? And the limit as x approaches negative infinity, what's happening to your function? Now this is important. We're only talking polynomial functions here. So how do we determine the end behavior? We're going to use what's called the leading coefficient test. You're going to look at the leading term and you're going to look at its power. So consider the polynomial function here. Okay, so a sub n, a sub n minus 1, a sub 1, these are all coefficients. They're numbers being multiplied to variables. And remember, a constant term, a sub 0, has no variable. It's just a constant. And remember that the leading term of a polynomial is the term having x to the largest power. So this is kind of a refresher. So we're going to use the leading coefficient test to determine end behavior of functions. Now remember, like I said, there's only 4 choices here, and we're going to use those. Okay, so let's get started on this. Okay, so use the leading coefficient test to determine the end behavior for each graph. So I'm going to go ahead now and look. So it's the leading coefficient test, okay? So if I just rewrite my polynomial here, I could say, well, I'm just going to rewrite it in case I mess up. Okay, so I have 4x to the 5th plus 6x cubed minus 2x squared plus 8x plus 11. Now this is in standard form. We're starting with the largest power, 5 to 3 to 2 to 1 to no. So there's your constant. Remember, these are the coefficients, the numbers being multiplied to the variable. So you use the leading coefficient test. So here we are. We look there. And now if I look back at my samples, I have n is odd, meaning the power is odd, okay? And a sub n, the leading coefficient, is positive. So if I look here at my examples, I have n being odd and a sub n being positive. So I have down, up, end behavior. So the end behavior of this function is down, up. And now let's also describe it as a limit. So if we describe it in limit notation, we could say the limit, okay, as x is going to infinity, okay, so as x gets really big here, y is going to infinity. Our function is going to infinity. And the limit as x goes to negative infinity, well, that's going down. The y value is going down, so that would mean negative infinity. Okay? So the end behavior is down, up, And in limit notation, it's here. Okay, so notice how when you go to negative infinity, it's down, going to negative infinity, and up when a goes to, or x goes to positive infinity. So that's the first one. Now let's go ahead and look at the second one here. Now this one's a little out of order. Okay, so you have p of x equals 5 plus 2x minus 6x squared. So let's look at the degree. You might say, oh, here's the leading coefficient. No, it's not. You got to look for the term that has the largest power. It's not there. That's a 1. There it is right here. So we know that n is even. Okay, n is even, and a sub n is negative. Okay, so we look at our paper here to help us. N is even, and a sub n is negative. My n behavior is down, down. Okay, so I would say the n behavior here is down, down. Okay, so in limit notation, I could say x is approaching, well, it doesn't matter if x is going to positive or negative infinity, our function is always going to negative infinity, and that's instead of writing both terms out. Okay, so there is the n behavior for part B. Part C here, we're looking at h of x equals negative 2x cubed plus 4x squared minus 7x plus 9. That is in interval notation. Or excuse me, interval notation. I'm sorry, in standard form. Okay, so we've got that one. So let's go ahead and look at what's going on here. We're going to run out of space, so I'm just going to write on the original sheet here. So let's look at, we know that a sub n is negative, and the power is odd. So we would look at our sheet here and we say odd power, negative a sub n, it's up, down, n behavior. Okay, so we would say up, down, n behavior. So that means as the limit of x goes to negative infinity, f of x goes to positive infinity, and as the limit as x goes to positive infinity, the function goes to negative infinity. And think about that from the picture here. Okay, look, as x goes to negative infinity, as we go this way, the y values are going up. So it's positive infinity. As x goes to negative infinity, the y values are going to negative infinity. And there's that term. Okay? So that is n behavior of a function in both interval notation, interval notation here we can call that, I guess, and also in limit notation. So if you have any questions or comments, let me know, guys, and we'll see you next time.